those people who know science do not know what technology is, and those people who know technology or who learn technology don't give importance to understand science, right? So I just thought that it is interesting to meet graduates, right, who are called to be the future technologists, right? Because when they understand science in a very proper manner, right, they can develop the technology very quickly. This is a very good example for that, right? And of course, the lasers can be classified into various categories according to the wavelength, right? Infrared, visible, ultraviolet, and they can be called as continuous wave and pulsed wave, right? And you all know that L stands for light, and this is the electromagnetic spectrum, which we call it as light. 2 X-rays and gamma rays, right? And there are n number of lasers available in these 3 domains: infrared, visible, and ultraviolet, right? And of course, as we have discussed, microwave lasers are available, right? This comes in this particular domain. Electrical wave lasers are actually possible, but they are not of interest because they are longer wavelength. They can carry only shorter, smaller amount of energy, all right? And at this particular junction, I will ask you to again to ask to yourself, is it possible to have a light source, right, in X-rays and gamma rays? Do we have any X-ray light source or gamma ray light lasers, right? The answer is no now, because you all know that for a laser to work, you need 2 mirrors in between the light has to reflect. There is no material which can reflect X-rays and gamma rays 100%. When such a mirrors are going to be identified in future, X-rays and gamma ray lasers are going to be possible, and when they are going to be evolved, right, it is going to be a game changer, all right? So lasers are mostly available in ultraviolet, visible, and infrared, right? And when you have a close look at the different type of lasers available, you will see that infrared lasers are commonly available from this particular light source, right? T sapphire, helium, neon, NdArc. And when you have a look at this particular type of lasers, we normally call these lasers as solid lasers, because a NdArc has a crystal in which a stimulated emission takes place, right? So the optical medium, if it is in solid state, we call them to be, right, a solid laser, all right? So most of the infrared lasers are generally created from solid light sources. And when you go to visible light, right, you will see that, I'm sorry, right, I have missed something, right? When you go to visible light, right, you can see that they are mostly created from liquids, you call it as dyes, right? And of course, after the invention of semiconductor lasers, there are more number of light sources available, right, in the visible domain. But keep in mind, semiconductor lasers cannot create high power lasers. And of course, there are fiber optic lasers. And beyond visible, if you go to ultraviolet domain, still there are light sources which are created from helium, cadmium, nitrogen. Of course, CO2 is exempted here, right? And there are many laser sources available. When you have a look at these light sources, you will see that all gaseous form. So ultraviolet lasers are also available. They are created from a gaseous modem, so which makes this laser very complicated to handle, right? Because when you have a gas, right, in a laser, it will be always very difficult to port them from one place to another, right? So even though ultraviolet lasers are available, it's very difficult to handle because they are gas lasers, right? So I will leave one note for an engineers, right, which I often talk to my students as some science graduates, right? It is very pathetic to tell me very sadly that all the lasers that are replaced in India are not manufactured here, they are imported, right? So you can seriously look for those people who want to be a real technologist, right? With concepts like Make in India, you can be an entrepreneur, right? If you can develop a lab that can create lasers, right, you will become a billionaire in very short duration of time, right? So I will make a note to this budding engineering graduates to think in these type of domains. Of course, since the time was very limited, I'm going a bit faster, right, to give you more information. I have given you one first information for you, right? I have given you some basics of lasers, right? And from that particular laser, as a science graduate, I have left you a message that, right, lasers are imported and they are not manufactured, right? And in the beginning slide, I will go to the next part. The beginning slide, we used a term called as illuminating the room with the light, with the lasers. Right? You all know that for illuminating a room, you need white light. Right? But when I say white light, you will not accept it to be a laser because laser unique character is that it is monochromatic, which means that they have a single wavelength. Right? But white is polychromatic, it has different wavelengths. So if someone asks you, is there any white laser possible? The answer is going to be yes, because by mixing different lasers, the primary colors like blue, green, and red, it is possible for you to create white lasers. You could see a fiber optics here in which three particular light sources, red, blue, and green, were coupled in a fiber optics, and the light that is coming out of the fiber optics is going to be white in color. All right? And since it is going to be polychromatic, to get coherence, it has to take a duration of space, and that is the reason why it is called a supercontinuum. White laser is not a new term to science because it is already being technologized, right, in BM8W, right, BMW i8 series, in which white lasers are used for long-range visibilities. All right, so white lasers are available in market. I want to mention you because we were studying, right, in our graduation that laser is monochromatic by nature, but technology has taken us to the next level that lasers can even be polychromatic, right? So white lasers are available, right? And to make you to get still a better understanding, right? Lasers are everywhere. And Mayman, when he introduced laser, he called a laser as a solution looking for a problem, right? Because whenever we take a problem to laser, it gives always a solution. Say, for example, when communication was very slow, right? When people asked, do we have a solution? Laser gave a very interesting solution called as fiber optic communication. And most of the communication that are around us, almost 100%, works on the phenomenon of fiber optics, right? And you can extend this application to n number of applications. Holograms, right? 3D technologies are going to be the future printing devices, right? It works on the principle of laser. And you could see this one. This is called a CD disk, right? Before that, there was a floppy disk. And nowadays, we don't have any CDs. We have DVDs. And I will say even we don't have DVDs, now we have Blu-ray disc. All this particular technology evolves, right? Because lasers are used to read and write, right? And in the same way, if you go to material processing world, right, lasers are nowadays used for welding, right, cutting, and all those particular purposes. Aeroplanes, ships are actually built not with human-made weldings; it is through laser weldings, right? So, automobile industry are already being ruled by laser. And when you get to medicine, right, bloodless surgeries are nowadays possible, right, because of these lasers, right? And what I have shown you is a cataract surgery that was done through lasers. It was a major surgery, right? It has become a minor surgery nowadays because it has turned out to be bloodless surgery, right? And I can increase the list of lasers application, right, like this, right, to n numbers. And the future laser technologies that is going to be soon possible is, right, nuclear fusion reactors are going to be soon possible, right, through optical molasses, right, which works on the phenomenon of trapping atoms or molecules with lasers, right? And when this is going to be demonstrated successfully, nuclear fusion reactors are going to be available, right? And the technological applications are not only limited for lasers. Nowadays, lasers are used for destructive weapons also. Each and every country has a new division in its army called as DEW, right? Directed Energy Weapon, and they call it as LDU, right? It is Laser Directed Energy Weapon System, right? Imagine you have a spy satellite upon our country. If I hit them with a missile, it is an international problem, right? Imagine I have an infrared light, right? A laser, right? You all know that infrared lasers are invisible. And if I focus that infrared light laser upon that particular spy satellite, right, through its heating effect, it can destroy that particular spy satellite, right? We call these as dazzlers, right, directed energy weapon technologies, right? And such a technology is already available in all the countries, which are called to be developed and developing, right? And India even have that such a technology, right, called as DUE, right? And lasers are not only used for constructive purposes, they are being right used in defensive domain also, right? And lasers are actually unavoidable, right? And as I have mentioned you, lasers are available in a wide spectrum, but still then people are looking for short wavelength lasers. I will specifically confine myself with UV lasers, which cannot be directly engineered from a solid state device. As I have told you, UV lasers are although available, right? They are gas lasers. You cannot create any UV light, UV laser light from a solid device, all right? So people are looking for generating short wavelength lasers in indirect manner, all right? And that is a place where the domain of nonlinear optics, a new science comes to the picture, which I will right introduce you to think beyond your box, right? To think beyond your books, all right? So lasers are not only for technology, but also it is for very interesting sciences behind it, because whatever that we know about light is just 5%. And when laser was evolved, people understand that 95% of the light domain was still undiscovered, right? And when laser was invented, the entire field of optics was divided into linear optics and nonlinear optics. I have just given you a few examples to make you understand what is non-linearity is, right? Even though there are n number of application examples here, people marching and the lightning, right? This is linear, this is non-linear. This is simple harmonic motion, this is an unharmonic oscillator. The wave that is created is linear, this is non-linear. To make you to still understand in a better way, I will ask you to compare yourself traveling in a giant wheel and a roller coaster, right? The travel that you have in a giant wheel is going to be a linear process, cyclic, right? But a roller coaster, you all know that you cannot expect what is going to happen next, right? You can expect only unexpected things to happen. We call these particular processes non-linear, right? So there is a world called as non-linear, as I have mentioned you in the beginning of my slide, right? This world is not linear. The same is the case for optics also. When laser was invented, the entire domain of optics was divided into two branches. One was called as linear optics and the other one was called as non-linear optics. And one simple differentiation is that all the phenomena that were known to you already, something like absorption, refraction, polarization, right, are nowadays right, called as non-linear absorption, non-linear refraction, non-linear polarization, etc. Right? So there is a separate domain called as non-linear optics, right, which I will introduce you in a very short span of time. I don't want to discuss much of science for you and bore you. All right, if someone asks me what is nonlinear optics is all about, right? So nonlinear optics evolves when a laser light interacts with the matter, right? When a conventional light interacts, right, they create linear optics. When a laser interacts, they create nonlinear optics. If you want to differentiate these two, I will ask you to compare these two situations. In these two pictures, you will see the case of line is a bit complicated. Right? If I ask you who is stronger in the first picture, you will say lion, because a lion chases a zebra. The second case, you will see that elephant looks stronger than lion, right? Right? And if someone asks you, is this lion is brave or coward, right? You will say that the situation actually decides. The same thing has happened in science also. When a normal light interacts with the light, atom, right, it was something like a competition between zebra and a lion, right? So the photons that were coming from a conventional light sources, when they interact with the atom, it was something like a fight between zebra and a lion. But when laser was introduced, right, it was not like a conventional light source. It was very stronger, right? And suddenly the situation has become, right, a competition between elephant and a lion, right? Suddenly, this atom becomes very weak in front of this particular lion, right? And as a result, a new term introduced was evolved, which we call it as nonlinear optics, right? The reason is going to be very simple. The atom, you all know that it is made up of protons and electrons, and there is an electrostatic field between them. The protons and the electrons are held together very strongly through an electrostatic field, and the value is generally in the order of 10 to 7 volt per centimeter. And you all know that light is the electromagnetic spectrum. And if you calculate the electric field associated with any conventional light source, it will be in the order of 10 power 3 volt per centimeter. So if I ask you whether 10 power 7 or 10 power 3 is greater, you would say 10 power 7 is larger. All right. In the same way, right, if you calculate it for laser, the conventional electric field associated with laser is 10 power 10, which becomes very much higher than, right, than an electric field that prevails between an atom. Right. So this is the thing that has happened. Right. Earlier, the electric field carried by light sources, when they interact with the light, with the atom, was very weak. As a result, atom dominated the entering photons. But when a laser falls on an atom, since they have a very stronger electric field, they started dominating the behavior of atoms. As a result, the optic has suddenly become nonlinear, right? And we call that particular branch as nonlinear optics. As a result, what happened is plenty of new phenomena arise, right? You all know that polarization, right, is the phenomenon in which multiple direction light is confined to one single direction. But you all know that when a yellow light is allowed to pass through a polarizer, you will be getting only yellow light coming out in a single direction. Imagine if I send a yellow light and a blue light is coming out, right? You cannot call that one to be in polarization, right? But such a things are going to be possible, which we call it as nonlinear polarization. And we all know that absorption is the process in which electron absorbs one photon and they move to excited state and they get back. Right? Imagine instead of absorbing one photon, if an electron absorbs two photons at a time, you call that phenomenon as, right, two photon absorption, and we call that phenomenon as a nonlinear absorption. And in the same way, when a light refracts, right, it actually moves from rarer to denser, right? As a result, it deviates. But when a laser is allowed to pass through a medium, it makes the medium to behave like a lens. As a result, what happens is refraction becomes nonlinear, and the light laser that travels through the medium, either they converge or diverge by themselves, right? Which we call it as nonlinear refraction phenomena, right? Just to give you one more point of clarity, right? If you take this equation, this is called as a linear polarization equation, in which P is proportional to E. It's a straight line. But in this equation, I have added the higher order terms. As a result, what happens is polarization versus E is not a straight line. It is going to be nonlinear, right? So what happens as a result is when you expand this equation, you will get some equation like this, right? And when you expand this equation, you will see that, right, a lot of new phenomena arises, right, which we call it as harmonics of the fundamental light. I will talk about this one in a different sense, right? So what do nonlinear optics has given us is that, right, it has made us to think out of box. Not all your absorption need to be linear, it can be nonlinear. Just to give you an understanding, if I ask you, can a red bulb emit blue light? Or a blue light can emit green light? The answer is going to be no, because it is going to be monochromatic. But in nonlinear optics, a phenomenon called as frequency doubler is available, right, in which a light of one frequency can be converted to another. Right? So what you see here is a linear process. A white light falling on a green slab will be giving you only green light coming out. This is a filtering process, and this is mere linear absorption. But in nonlinear optics, there can be phenomena like two photon absorption. Imagine you have a material that absorbs two photons at a time, right? So when a electron absorbs two photons at a time, right, like this, and if they emit the particular photon together as one single photon, its frequency is doubled. We call this material as frequency doubled material. So what happens as a result is, apart from the light you have sent, whose frequency is omega, there is a possibility of getting one more light whose frequency is 2 omega, right? So here frequency is double because of two photon absorption, and we call this phenomenon as frequency doubling phenomenon, right? As a result, what happens is, not only the light that I have sent is coming out, a new light is coming out, right? A new blue light is coming out, which was not actually sent by you, right? People was very surprised to see that. And Franken is a scientist who demonstrated the first successful experiment on this in the year 1961, exactly 1 year after the demonstration of first laser. And after that, the concept of laser actually evolved, right? And people started fabricating, right, short wavelength lasers using this particular technology. As I have told you in the beginning, most of the solid state lasers emit infrared light, and there is a demand for short wavelength lasers because they are produced only from gas lasers. As you have seen in this picture, right, when a frequency doubling takes place, the frequency gets doubled. When the frequency gets doubled, you all know that the wavelength reduces by half, which means that when I send a longer wavelength, there is a possibility of getting shorter wavelength. All right. So look at this particular example. It has a very interesting engineering behind it. This is NDIAC laser. An NDIAC laser emits 1064 nanometer infrared laser, right? So infrared light is coming out, and in this particular chamber, I have placed a crystal, which I call it as a frequency doubler. You all know that what do frequency doubler do? They double the frequency, which means that they reduces the wavelength by half. So when I divide 1064 by 2, you will get 532. You all know that 532 is nothing but a green light, right? Look at this case. Even though infrared light is coming through, after your frequency doubler, you are getting a green visible light coming out. Phenomenon in terms of science of second harmonic generation. And a very interesting technology is that NDIAC is not only capable of emitting 1064 infrared laser, with this technology, it can even emit 532, right? And this is the technology now, it is being used to generate short wavelength lasers. Just to make you to understand why short wavelength lasers are in higher demand, this picture is a very good example. As I have told you, nowadays we have Blu-ray disc, right? We don't have any DVDs. The answer is going to be, right, is here. As the wavelength of the laser is getting reduced, you will see that the spot size, which we call it as the diameter of the laser, when it falls on a medium, it gets reduced. As the wavelength decreases, the spot size gets reduced, which means that if I want to read or write a CD, right, if I use an infrared light, I can write only specific amount of data, but if I use ultraviolet light, I can read and write more number of data, right? And this is the technology that is being used in Blu-ray disc because they use blue lasers instead of red lasers, right? DVD works on the phenomenon of red laser for reading and writing, whereas a Blu-ray disc uses blue lasers to do this particular process, right? So shorter wavelength lasers are in demand, and to create shorter wavelength lasers, engineers used a technology, science called as frequency doubling, through which, right, a longer wavelength can be converted into shorter wavelength, right? So with this particular glimpse, I will get into the final core of my discussion, right? The most needed technology, what people are around us in this pandemic situation. You all know that UV lamps are in high demand, as like your hand sanitizer, mask, right? In a very short interval of time, all the future home technologies, right, will rely on these UV lamps, right? And all the hospitals already have users, and there will be UV lamps in future also, because they can fight against the viruses very effectively, right? So the reason is going to be very simple, which I will explain it in the next slide. What you see here is the UV lamps, right? So when a UV lamp is placed in the hospital, right, it can kill the viruses all around us, all right? So this is the technology that has been used in hospitals, in many multi-specialty hospitals. There are UV lamps already, right? And there are UV sterilizers. You all know that UV sterilizers are used to sterilize the medical components used in hospitals, right? And this UV sterilizer is available in market now, right? Which is used to sterilize your mobiles, right, and all the particular goods that you carry, right, in pandemic situation. Say, for example, I take a purse. When I get back, I may be afraid that, right, there may be virus with the virus in that particular purse, right? I want to clean them, right? Use UV sterilizer to do that particular process. Kill viruses. If you ask me why, what is the science behind it? The reason is going to be very simple. When ultraviolet light falls on a virus, what do they do is, the energy that is associated with ultraviolet light is very large. So what do they do is, they break the cell wall of the virus and that damages the DNA. As a result, what happens is, this virus cannot reproduce themselves. As a result, they kill themselves very easily. All right. So UV lights are used to kill viruses through this particular technology. And when you have a look at the electromagnetic spectrum, you will see that ultraviolet C category, which we call it as this domain, right? Between 200 to 280. To be more specific, it is 264 nanometer, all right? So when a light, UV light with the wavelength 264 nanometer is passed through virus domain, they can kill the viruses very effectively. So people are looking for this particular UV light all around, all right? And the reason for using UV light to kill bacteria is that they can kill the viruses very effectively. So someone can ask me, right, what happens to the humans when we are irradiated with UV light, all right? Can they harm humans, right? Very interestingly, the answer is going to be no. Because when a UV light falls on skin, right, they cannot harm the human skin because those dead cells which are available upon the top layer of the skin will not allow the UV light to pass through. In the same manner, when you look upon a UV laser, right, through your naked eye, they are not allowed to permitted to enter your eyesight because thin layers of our eye will absorb that. As a result, what happens is UV light can kill viruses, but they are harmless to humans. As a result, what happens is UV lights are nowadays used to kill viruses, and there are scientific reports that H1N1 virus, right, was effectively killed with UV light when its energy is in the order of 2 millijoule per centimeter square. But producing these type of lasers in the form of laser is very complicated because recent report shows instead of using UV LEDs, if you use UV lasers, the process can be very effective. But problem is you don't have any UV lasers emitted from from a light source because as I have told you, UV lasers are generally produced by gas lasers and semiconductor lasers only produce visible light, and UV lasers cannot be produced directly from any of the materials. Right at present, worldwide, this particular technological development is being processed. Take a frequency doubler, right, which we call it as a 2-photon absorption, as I have told you in the beginning. Put it in front of a light, say for example 440 nanometer. Gallium nitride, right, is a semiconductor laser which emits 440 nanometer. If I put a frequency doubler in front of it, it will reduce the wavelength by half, which means that the light that is coming out will be 220 nanometer. All right. So this is a very interesting factor that when this particular light is available in the form of laser, they can kill the viruses very effectively. All right. So these type of technologies are now being developed all over the world, right? Which we call it as laser UV sterilizers, which is going to be soon in market, right? In future sense. All right. I will take this particular point to be my end note. Right. There is a very big gap between science and technology. As I have told you in the beginning, we as a scientist believe that our duty is to study what is science is all about. We explain what is nonlinear optics. We explain what is stimulated emission, what is 2-photon absorption. But we do not know how to transform these science phenomena into technologies. Unfortunately, what do technologists do is they learn how to develop devices, but they don't understand the science. All right. Look at this particular case. If there are someone who are good in science and technology together, right, if they can couple this frequency doubler, right, with their particular technological knowledge, right, these type of devices can be created instead of UV LEDs. UV laser technologies can be realistically